Okay, we'll get started. Greetings, everyone. A very warm welcome to you all to this webinar hosted by the North Central Climate Adaptation Science Center, also called the North Central CASC, which is based at the University of Colorado Boulder. I'm Imtiaz Rangwala, climate science lead at the North Central CASC, co-hosting this webinar with my colleague, Christy Miller-Hesed, who is our regional climate adaptation scientist. We bring you these webinars to facilitate a discussion of science, research, and best practices related to adaptation and resource management under a rapidly changing climate, with a focus on the North Central US that encompasses the Missouri and the Upper Colorado River basins. Before I introduce our speaker, a quick word on housekeeping. We are recording this webinar, and you can find all our webinar recordings on our website. During the webinar, all participants will be muted, but you will have the ability to unmute during the Q&A period at the end. We, however, encourage you to put your questions and comments in the chat box anytime during the webinar, and we will start with those questions first during the Q&A in the order they are received. We will end the formal part of this presentation at noon Mountain Time and stop the recording at that point. After that, anyone who wishes to stay on to engage in a more informal conversation with our speaker is encouraged to do so. And now I'm very excited to introduce Dr. Jilmarie Stephens, our speaker for today. Jilmarie is a biomicrometeorologist. Maybe I'll say that again, a biomicrometeorologist studying ecosystem-atmosphere interactions in a changing climate, from surface layer turbulence to ecosystem scale climate, carbon balance, and wildfire regimes. Jilmarie received her bachelor's and master's in atmospheric science at UC Davis and her PhD in soil science from the University of British Columbia. Her doctoral work focused on long-term trends in boreal forest ecosystems using both flux tower measurements and ecophysiological modeling techniques. She also studied the impact of an insect infestation event on the carbon and water fluxes at an aspen stand. Her postdoc at North Central CASC and Earth Lab is part of the CASC Climate Adaptation Postdoctoral Fellows Program focusing on the future of fire. Her current research focuses on understanding changing wildfire regimes across the US under different future climate scenarios using historical fire and climate observations and numerical modeling for the projected climate. Her talk today is titled Fires of Unusual Size, Future of Extreme Wildfires in the Continental United States. Well, thank you, Jilmarie, and please take it away.
All right, thank you for that introduction. So yes, as Imtiaz said, I'm a postdoctoral fellow with the National CASC doing a Future of Fire postdoctoral work. And then I am the fellow for the North Central CASC. And this is my regional project during this postdoctoral fellowship. And so again, I'm looking at fires of unusual size, fires across the continental United States. There we go. So as you guys know, we have become used to these titles of US fire size becoming larger, more frequent, and widespread since the 2000s. We've seen that record fires occurring in 2020. So we saw that some papers talked about record-setting climate enabled this extraordinary fire season. And so with these fires, there's been research talking about the changing risk and burden of wildfire across the United States. And specifically in the Forest Service, they have new information and packaging talking about confronting the wildfire crisis. So that's where we are in terms of wildfire across the United States. So some of these trends in fire across the United States, we've seen over the past 4 decades, burned area has roughly quadrupled. So we see the burned area trend is 70,000 hectares per year, increasing from 95 to 2020. And then some of these causes are, we have an increasing trend in fuel aridity. So we're seeing drying of the vegetation on the landscape. We've seen more houses built in the wildland urban interface. So now there's approximately 49 million residential homes in this space. We'll talk about why that's important more in a couple slides. And because of all of this, the firefighting costs have increased at a rate of $60 million per year. And in the last couple of years, it's been at a rate of $3 billion per year. So why the wild and urban interface is so important is the WUI, as it's called, is the area where houses are in or near this wildland vegetation. And so as houses are built in this area, what happens is native vegetation is lost. It's fragmented by the introduction of homes and the landscaping. And that landscaping introduces non-native vegetation. So we disturb the soils and we cause these non-natives to spread. And so the figures on the left, you can see that sorry, my dog, the WUI actually, it only occupies less than 1/10 of the land area in the continental United States, but we've seen a trend increasing in this WUI land since 1990 through 2010. And 43% of all new houses were built in this WUI land, but this WUI land, 61% of it was already considered WUI back in the 1990s. So it's not that we're expanding significant area, but we're building more houses in area that was already determined as WUI. So again, why housing in this area matters is, unfortunately, humans start most of the fires. So where human settlement is, we're more likely to have ignition. So humans ignited 4 times as many wildfires as lightning across the United States. And lightning is responsible for the majority of the fire in the western area, so interior. So what you see on the left is all the red is showing the human ignited fires and large fires. And then down here, we're looking at the mean fire size. And what we see is the number of fires ignited by humans. There's a lot more at a smaller size. And so there's a longer tail by lightning. But unfortunately, again, humans are starting most of the fires. And again, when we talked about the WUI, we talked about invasive species, introduction of non-native vegetation. And so this study looked at invasive grasses in fire. So they looked at 29 ecoregions across the United States and 12 different species of grasses. And 8 showed significant increases in the fire occurrence. 2 showed significant increases in mean fire size. And 6 showed significant increases in fire frequency. So all of this non-native vegetation we're introducing is altering the fire regimes across the United States. And then also, there's been a history of a west-wide focus. As we saw in the papers, a lot of the large fires have occurred in the West. So a lot of the research has been focusing on trends in this Western, which we're considered part of the Western region. And so in terms of attributions to what we see here, forest fire area, to fuel aridity, the impacts of like temperature, precipitation changes, a lot of that has been thoroughly studied in the West, and unfortunately, a lot of the East has been neglected. So some of the other work that's been projecting future fires, as I just mentioned, there's a lack of information for large parts of the U.S. that have been designated like unburnable due to vegetation, agricultural practices, so the amount of irrigation, and or that there has been a lack of fire in the recent history, so that there isn't enough fire events to build models on. And so hence, like the figures on the left, you see there's large fractions of the United States that have no model developed for that area. And then also a lot of these past work only incorporate linear relationships. And what we've seen is with climate and fire, there are a lot of non-linear relationships. And then also a lot of these don't have any of the anthropogenic ignition signals. And as the beginning of my presentation showed you, people start most of the fires, and where people are, we're going to have more ignition. So knowing where people are is important for capturing the future fire signal. So that gets to my work. So it's based off of previous work by Joseph et al. He was a postdoc in Jennifer Balch's lab, who is the PI on my project. And so he looked at predicting wildfire size extreme using Bayesian statistics. He tested multiple fire, 4 models for the fire occurrence, 5 for fire size. And so what we see here is these are the best results of the models he tested for predicting extreme fire sizes. And so I carry those forward. So these are the models that I use to predict future fires. So going into our data. So the training data, we use GridMet data, which is 4-kilometer resolution meteorological data from the past. My initial observation starts in 1984. Obviously, this says from 79. We're not using the full period. And for the future, we're using the market data. And so that is this multivariate adaptive constructed analog. It's downscaling of the global climate model. There's the RCP 4.5 and 8.5 out to 2100. We decided to only do out to 2060 because that was the period that fire managers were more interested in. So we're not using the end of the century. And because of that, we're actually only using the RCP 4.5 because the divergence between the two paths doesn't really start to happen until after 2050. So we're only using the RCP 4.5. And of all those models, we did not use all 20. This is a ranking from the Forest Service report where they actually got the model performance results from this Rupp et al. And so we wanted to take the top 10 based on this analysis of the relative error of all the models across the United States. But unfortunately, 2 of them were missing the minimum relative humidity variable that we need to run the model. So I ran 8 of the top 10, and those are all the ones with the stars. Okay, so for our fire data, we use the monitoring trends in burn severity to get our fire occurrence and our area to tell us the area burned. And so again, this MTVS data set doesn't start until 1984. So that's the beginning of our training period. And they say till present, but there's usually a lag of 1 to 2 years. And when I started this analysis, I had till 2019. So that's the end of our training period with the fire data. And then the last thing, as I said in the beginning, is we include the human ignition source. So we use population density. And so I got this from this integrated climate and land use scenario, the 4th National Climate Assessment. They use the shared socioeconomic pathways, which are similar to RCPs, but now they include the social economic technology trends. And so the one we chose was the SSP2, which is like the middle of the road path. And so in this, for population, they have migration, obviously mortality, births, all of that to help predict the population. And so as you can see, most of the cities that already had high population in the past, as we project to the future, just become more dense. And then, so our model is run at the level 3 EPA ecoregion scale. This is the D, so there's 84 ecoregions, but the ecoregions are, so there's level 1, 2, and 3. And our model actually allows for a hierarchical approach where some of these regions have had 0 fire events in the past, or maybe 1. And so to develop a model for there, the fact that these regions are in level 2, level 1, we actually have cross-level sharing of finding similar ecoregions that have similar vegetation, obviously like climate paths. And so we can actually share cross ecoregion information to help predict models for places that haven't had many in the past. So this is something novel about our approach in the modeling. So I've shown you, we have our training data I showed you the NTVS from 1984 on. The reason I cut off the beginning or the end of the 80s is our ichthys population data set doesn't go before 1990. So I start my training period from 1990 to 2019. So we have our GridMet data, we have our population density, and we have our MTDS giving us our number of fires in our burn area. And then for our future inputs, we have the MACA data, and then our future population projection from the ichthys data. And so all of these data are obviously at various scales, time steps. And so the first thing is we have to summarize all the data at monthly time steps and at that EPA level 3 ecoregion. So I get every ecoregion has a monthly average precipitation, relative humidity, population density, all of that. So once we have that, we match the number of fires in an ecoregion. So we count the number of fires per month, we sum those up, and then we actually create our like splines that go in for each variable. So we allow degrees of freedom. As I said, there's cross ecoregion level sharing. So by the time we've done that, we include the terms for each of the 3 ecoregion levels. We actually have 3,000 terms that go into each of our models. And so we run the log normal for our burn area. We have that zero inflated negative binomial for our fire count. And so we run each of those for each of the 8 MACA models. And so I want to show you some of the nonlinear effects of our variables that go in. So we have the 6 main variables. As I told you, we have air temperature. So this was housing density, which obviously maps to our population density. So that's what I use. This was Max Joseph's work. We have precipitation in 2 forms. We have the same month precipitation, and we have the sum of the previous 12 month precipitation. And that is kind of to give us a sense of the aridity that we saw before, because it's letting us know how much moisture has occurred in the previous year. Then we have our minimum relative humidity and wind speed. And so you can see here in this graph, all of those lines, they're grouped by the level 3, the level 1, ecoregion. So there's only 10 of those. So the reason you see so many lines is because all the level 3s are obviously within that level 1. And so you can see there's various nonlinear relationships that are different between the temperate forest, different between the Great Plains. So we have not the same, obviously, climate influence across the United States. But one similarity is the strongest driver across the United States was the minimum relative humidity. Next was the maximum temperature. And then we had followed by wind speed and the 12-month precipitation. And the hierarchy of which one comes with wind speed and 12-month precipitation is variable between the 8 models that I ran for the future. And so, as I said, there's unique effects at that level 3 ecoregion. So we see that the Great Plains, the expected number of fires in cold conditions is actually higher relative to others. And so you can see that happening here in this hump right there. So when it's colder, we're actually having more fires in the Great Plains than these other the other regions there. And then the increasing this 12-month precipitation in the North American deserts. As we get more precipitation, obviously we're allowing more vegetation to grow, we're having more fires. So there are unique responses to climate happening across the United States. So looking at the future, so these are the 8 models that I showed before. So this is the mean from the 2020 to 2060 relative humidity across each of the models. You can see broadly they have very similar color schemes, but there are slight differences in that some models have higher relative humidity projected flowing all the way down the Mississippi River, so the IPSL and the CSIRO, but the Hadleys, they do not. You can see that, but there's lighter. And then the MRI has significantly higher relative humidity in around the Great Lakes. So there are slight differences, but like I said, the overall patterns are the same. And so these slight differences per ecoregion will come out in the future when I show the model results for the fire. So next, the next biggest impact was the maximum temperature. So this is again the mean of the 2020 to 2060. And unlike the relative humidity, the patterns are even more similar across, except for the Canny ESM2. That model you can see in the northern tier of the United States actually is much colder than the rest of them. And again, these slight variations come out in the future fire modeling results. And then the next one was the previous 12 months precipitation. And again, this one, they're all quite similar. The IPSL has a higher precipitation here in the mountains for some reason, but overall very similar patterns. And the last one is this mean wind speed. And of all the variables, the mean wind speed is the one that has the most differences among all of the models in the future. So you can see like the MRI model has significantly higher wind speed in the Appalachians, and then again along the Great Lakes. And other ones, we can see like higher and lower mean wind speeds in various parts of obviously the West. So there, again, like I said, the reason I'm showing these is because these slight variations will come out when we look at the future fire modeling. So CONUS-wide first, before we get into the details of every individual ecoregion. So we have the MTVS observed the full record 84 to 19 burn area per year and number of fires per year. And then from that same data set, I'm using 1990 to 2019 because, again, that was my training period. And so when we look at how the model did, it actually does a really good job at modeling the full period from the MTVS. And then the key point here is when we move to the future, obviously there's quite a large increase in the number of fires per year and burned area per year. And so those results are the ensemble of all of the individual models. So the table on the right is showing you the burned area per year. And again, this is in millions of acres on the left, and then the number of fires per year. And what I'm showing you, the min and max, is each of these models had 1,000 iterations. And so we're taking the median output of those 1,000 iterations. But there's quite the range that was predicted from all of those runs. And so that's what you're seeing when I have the min and max. And as you can see, some key things to point out, which you'll also see in the future maps, is the IPSL and the MRI model, but specifically the IPSL model is about half of the other ones. So it's predicting significantly less fires than the other models. So I'm going to show you, go through a consistent pattern of these, looking at the change in fires per year, and then burned area, and then max fire size. So again, this is from the MTVS data set. This is the average fires per year from 1984 to 2019. So we can see the Great Basin, the Northwestern Great Plains, obviously some of the mountains in California are places that have had high numbers of fires in the past. And then when we look at the individual model run results for the future, as I just mentioned in the summary, the IPSL model is predicting actually a significant decrease in fires, whereas most of them are showing an increase, especially across the West. And so then when we do our ensemble average of this, we end up, this is our ensemble average for our future fires per year. And so we see for most of the United States, there's a slight increase. Obviously, in places that had lots of fires in the past, we predict those places to have a significant increase in the number of fires in the future. So we see again the Northwestern Great Plains, like I said, the Central Basin, the Northern Basin Range, and then Arizona and New Mexico Mountains. And then these regions in the Central Plains are some of the places where across all the models, there was a slight decrease. And so when we have our ensemble, there is a projection of a slight decrease of fires in that region. And again, the cause of that is different per model. And so, as I mentioned before, the main driver was the relative humidity, but then it's the maximum temperature, and then whether it's wind speed or previous 12 months precipitation, it depends on which model we're looking at. So this was the absolute change. Well, now we're going to look at the percent change in fire. So you can see that the pattern from the previous figures is quite different. So now we see the most red occurring in the east parts of the north of the United States. And the reason this is important is because, so when we look at our ensemble average, we see that the largest change in, so the largest relative change in fires per year, so our percent change, is in places that actually have had few fires in the past. So you see in the east, in the MTBS data set, most of them are in this 0 to 4 range. Whereas in the future, the fact that they even have a couple fires means the percent change is quite large. So these places that haven't had many fires in this recent past are going to start having just a couple more, and that's a huge difference for these regions. And so if we look at the change in burned area per year, so similar pattern in the MTBS record of the places that had the most frequent fires also had some of the largest fires in burned area per year. And so we see a similar pattern when it comes to the predicted places that are going to have large burned areas. And so again, when we look at our ensemble average, so again, the Central Basin and Range, the Northwestern Great Plains, and then the Arizona, New Mexico mountains. And then in the east, we see the southern coastal plains. So Florida is also a place that has going to have a large increase in the burned area per year. So just like we saw for the number of fires per year, if we look at the percent change in burned area per year, again, we see, so there are some models that show large increases in the north or along the Rockies, obviously, but the east is still one of the places that has the largest, again, relative changes, so these percent change increases in the burned area per year. And so now I'm going to focus on some key ecoregions that you heard me say frequently. So the Arizona, New Mexico mountains was in the top 5 ecoregions to have the largest increase in fires per year. It is the ecoregion predicted to have the largest increase in burned area per year. The Central Basin and Range, so the cold deserts were some of the places that had the largest increase in fires per year. And then overall for total burned area per year, the Central Basin and Range is the largest, is going to be predicted to have the largest burned area per year. Not the largest change, but the largest overall. And then one of the places, the southeast coastal plains had some of the largest absolute and relative increases in fires per year and burned area per year. And one of the ones I showed here that consistently had a projected decrease was the Central Appalachians. So it had a projected decrease of 10% in fires per year, and the Mississippi alluvial plain, so along the Mississippi River, was the place that was projected to have the largest percent change. So as you can see that in the past, it literally was one of the places that had one fire, and in the future, just having even less than a dozen, that percent change led it to be the place that is expected to have the biggest percent change in number of fires and burned area. So this place needs to start preparing for a future fire. So this is for the fires per year and burned area per year. Now we're going to look at the maximum fire size. And so to define the maximum fire size, we went with the 90th percentile max fire size so that we could have more observations than the one largest in each ecoregion. And so by using this 90th percentile threshold, that allowed a variable like size for the east and west, because again, as I said, some of these ecoregions have had one in the past, so their max fire size is literally just over 1,000 acres, whereas some in the west literally have had over 500,000, almost million acre fires within the observation. So by allowing that 90th percentile threshold, we can predict, variable sizes across the United States. And so the difference here is we see for almost all the models predict that the future, the 90th percentile maximum fire size will increase across almost all ecoregions in the United States. So when we look at the ensemble of that, we see that it almost mirrors the plot of the burned area in the past. So the places that have had really large fires in the past, again, Central Basin Range, Northwestern Great Plains, are going to have some of the largest increases in their maximum fire size in the future. So then if we look at the percent change, again, unlike the other ones that shows a lot of that percent change happening in the east, the largest relative changes are still going to even happen in the west. So basically the picture here is the west has had, the most fires in the past, the largest burned area, and they're expected to see the largest increases in maximum fire size in the future. And so some of these key places that I looked at for maximum fire size, we can see the past, the MTBS, and then the future. And so some people pointed out that the reason I chose this value for the future is to show the trend. And so the range we're showing here is the range in that 90th percentile max fire size. But with the Bayesian statistics, we actually have quite a range of probability distribution. And the reason I didn't show other ones, so we could show the 95th, the 97th, is that range then it ends up squishing the trend. And so you see the trend left. So while I'm showing you this, and it looks like maybe we're underestimating the future, it's just because I'm trying to show the trend in the observation that most match the past, but obviously the future could be significantly larger. And so again, I chose the Arizona New Mexico mountains. One of the places that showed the most increase was the California coastal mountains. So this is on either side of the Central Valley, and again, the southern coastal plains and the northwestern Great Plains. And so if we compare our results to other research, so we can see, as I told you guys before, we're doing out just the RCP 4.5 out to 2060. And so this paper shows that the future risk is pretty similar across the scenarios. They're doing the SSPs rather than the RCPs. But they also find that until about 2050, they're pretty similar, and then they start to diverge. But they also found that the high levels of fire risk in places like California in the West are starting to expand into new areas in the Western United States. And so then this paper, they use this physical chemistry fire frequency model, which models, as it says, fire frequency. And their model is only based on mean maximum temperature, mean annual precipitation, and then elevation. And so they also run at a monthly, and they projected the percent change in annual fire probability rather than actual fire count. And so they use the RCP 4.5 and 8.5. And you can see in their RCP 4.5 in the almost same period as mine, but 2040 to 2060, they see significantly less increases in the annual fire probability. And in their model, the temperature was the primary cause of increasing fire, whereas our number one is the change in humidity. And then again, other papers have looked at the likelihood of very large fires or the potential of very large fire weeks. And so we see that the highest ranking areas in terms of overall likelihood of fire are again found in the West, which is very similar to our results, where we saw for the maximum fire sizes that are going to increase most in the West. But as I pointed out, they show that the East, even though they have smaller overall likelihoods compared to the West, these increases are significant for those regions. So hence, the East has some of the largest percent changes in future predicted fire events. And so overall, the ecoregions that are predicted to have the largest fires per year are not necessarily the same as those predicted to have the largest burned area per year. Regions that had the most fires in the past are going to continue to be the most frequent burning areas in the future. But the southern coastal plains is one of the key places that's going to become a new frequent fire region. And although our model predicts like large relative increase in burned area in the east, the largest fires overall are going to occur in the west. And so CONUS-wide, we see a 56% increase in fires per year, a 59% increase in burned area per year, a 63% increase in that 90th percentile max fire size. And so overall, wildfires are spreading into regions where such events were historically rare in this recent past, and are leading to much larger wildfires in the west, where fires are common, but now the sizes are going to become unprecedented in these regions. So that is all. So time for questions. And also I have a special thanks to all my co-authors, which are Max, Virginia, Taita, Adam, Imtiaz is on my paper, Jane, and Jennifer. And these are all of our affiliations.
Great. Thanks so much, Jilmarie. That was a lot of good work. And so we have a lot of time for questions. I do not see any questions in our chat box, but at this point, you have the ability to unmute, even show your video if you like. So
do you want me to stop sharing, or I can keep in case people want certain slides to pop up?
Right. So maybe for a while you can get the slides there. Thanks, Jilmarie. So yeah, please go ahead if you have a question.
I've got a question. Hey, Jilmarie, thanks for giving your talk. It was great. Hey, I'm wondering how could you account for like fire vegetation feedbacks in the modeling approach, or if you think that they even matter at the ecoregion scale?
Yeah. So I didn't say that ours has no like fire limitation feedbacks of like reburns or whatnot. And so the only thing, and like that is a caveat of with the fact that we're not limiting like reburn potential in a certain place, which I think will have an impact, because obviously you can't reburn the same place over and over unless grasses can do it yearly, but obviously forests can't. But I know like John Obasugu's recent paper was saying like we haven't seen the limitation yet of like fire occurrence based on like burned area yet, but that was for the west. But I do think it will become important, and I know there are other papers. There is one that did have vegetation feedback, but unfortunately they found that despite that, they actually saw an increase in fire. There wasn't a mitigating influence. And so they even had more fire predicted events with the vegetation feedback.
Right. Right. Yeah, I can see it going both ways, right? Especially in places where you have invasive species coming in after a fire that might promote more fire. You might have a positive feedback, but in like more fuel limited systems, you might have a negative feedback.
Mm-hmm. And so and obviously we don't explicitly have vegetation. That's what like the ecoregions are, like as a proxy of like vegetation type. But there's a statement I was going there with that. Oh, is that like with the MTS data, like the training, like obviously we don't have any influence of suppression and whatnot, but obviously that record has suppression in it because we did fight those fires, and so because of that, like our training with our relationships and the nonlinearity that we allow, we think obviously is picking up some aspects of that, but obviously we aren't explicitly feeding that in,
Okay. Got it. Thank you. I've got other questions if nobody else has questions I'd love to ask, but I don't want to like dominate.
Go for it, Todd. Yeah, go for it.
All right. I remember when the original Maxwell Joseph's paper came out, and it's a pretty impressive modeling effort. If I remember it right, like so now I think modeling like wildfire occurrence and fire sizes is like one of the most challenging modeling activities you can take on. So way to be brave with the study, Jilmarie. What I see in a lot of papers is that the evaluations of the models and how well they perform is kind of lacking.
Mhm.
I think even in the original paper, I think Maxwell
Yes.
used coverage as a
So,
metric, which is great for showing like overlap between predicted and observed values, but it doesn't tell us like if they're correlated year by year or even like what the magnitude of the errors are. So I'm wondering if
yeah,
you can like comment a little bit more on like model performance, especially for years that weren't used to train the model.
yeah. So I actually did, and I didn't show any of that in here. But yeah, so like you said, in his original paper, he did like coverage, like, and so it was just like,
Yeah.
the model predicted here, the real thing wasn't here. And so before I even did all this, I actually did, like a withheld, period test.
Right.
And I actually tested again, because Bayesian statistics, there's the probability distribution. I actually tested the distribution that are output with the observed, and found that the median for the number of fires and fire size actually did quite well. And I did it across ecoregions, so you can actually see the scatter across the ecoregions, and so I have the names all plotted. And so yeah, I did some extra validation that I found necessary as well. And yeah, so those are my supplement that obviously weren't included in this.
Awesome.
Yeah, and so but then for the maximum fire size, that was the most tricky, because the way his it was like the block maximum taking the maximum in each year. And again, there was like the filtering that was done, he had to have at least 26 fires, and there's all these other things that, like, for mine to be uniform across the United States, I had to do quite a different approach than he was doing. So yeah, I can show you these other things later. But
Okay.
yeah, they weren't
Yeah,
included.
maybe I'll follow up with you
Yeah.
offline, but I'm glad that you did that. So thanks.
Yeah.
Thanks for the talk.
All right, I saw too. I think Dennis was first with his hand up, and then I know Phil did too.
Dennis, please go ahead. We can't hear you if you're speaking. Dennis, we cannot hear you if you're speaking. Perhaps we will go to Phil and then come back to Dennis. And then I have a couple more questions in the chat that we'll go to after that.
Oh, can you hear me now?
Okay, Dennis, we can hear
Yes.
you. Go ahead.
Wait, hello. My camera's not working, but anyway, sorry I got on the call kind of late, but I was interested in your presentation nonetheless. And yeah, I have to agree with you 100%. And also, we're on our third year of drought here in north central Montana. I live on the Fort Belknap Indian Reservation. And in the last 2 years, we've had 2 out of the last 3 years, we had significant fires in our Little Rocky Mountains. And I noticed it out in their field. It's really getting drier and drier, and yeah, it's outweighing our suppression efforts as far as thinning to
Mhm.
increase forest health by thinning and lopping, scattering our piles. We need to do a lot more of that and get our tribal community involved in that. They're pretty we need more outreach and education to get them on the same side as us to work. We just can't get them to work right now. And I think a lot of it has to do with all the wildfires in the United States taking our workforce away from us, because we
Yeah,
got
so-
work to do here on our reservation, but we can't get them until after fire season slows down in November or September, November, to get them back here to work for us in our forest.
Yeah, that's one of the implications I state, is that, like, I know, talking to different forest managers, they've talked about, like you said, when they're allocated man hours and resources, and obviously with the east gonna start having more fires, like a lot of the regions like don't have the same fire infrastructure as we are used to out west, and so like having to spread, like using resources over more areas is going to become more of a problem.
Yep. Thank you.
We can go to you, Phil, and then maybe we'll go to Kristen and Swata.
Okay, thanks. Hi, Jilmarie. Thanks for the presentation. This is really interesting stuff. And I likewise came in late because I was coming from my class, but so I might have missed this, but I guess I have a suggestion and followed by a question. And the suggestion is personally motivated, right? From the fire ecology perspective. I'd be really interesting to see these numbers in the context of a fire rotation period, or just because when I'm looking at these results, I'm wondering, like, are some of these regions going to cross these thresholds where the regeneration time of dominant tree species is going to be longer than the expected interval between fires or something like that. So I think your results can be really interesting in that context. And then my question is kind of following from that. Can you share any experience or any are the methods that you developed here, can they be applied at any smaller ecoregion scales? Because
so you mean down like further level, like level 4 level? Yeah, you definitely could. And then obviously you don't have to do the full United States, like that's just what we chose. And so like computationally, it's just obviously like the smaller you get, the more time it will take. But yeah, and obviously if you run more, like depends on how many models you're running, but you definitely can. You can definitely scale this down. And actually on that note, one of the projects I'm doing for Jennifer is we're transitioning this to a 4-kilometer scale. So it's going to be gridded now rather than ecoregion. And so yeah, there's going to be whole new stuff. Yeah.
That's really cool. And so I think those two together, and I know like there are kind of infinite uses and values for this type of work, but from the ecology perspective, that downscaling and then fire rotation period perspective can be lots of different uses. Cool work. Thank you.
Thanks, Phil. I'll go to the question on the chat by Kristen Emmett. So did you consider including additional fire data that would include smaller fires, since the MTBS only includes fire greater than 500 acres in the East? How do you think this may change results for the Eastern US?
Yeah, so we didn't. We used, again, I built off of like Max Joseph's work. So yeah, like what was the original decision of MTBS only? And yeah, it's true that I don't think I included like in the human versus lightning like slide. Chelsea Nagy, her paper, she actually looked at all fires. Yeah, and so like the distribution in the East, there are significantly more fires, obviously, that are much smaller. And her, I think it was, yeah, she used MTBS, but also something else to be able to do that, to look at more fires. And it just means that it's true. The number of fires that occur in the East will be significantly more because they have much smaller ones. And so I think that would change, obviously, the pattern that we're seeing there. But again, to do consistency across, we use the same like size cutoff. But I think it would just mean that there are more fires in the East.
Maybe I go to the next question by Swata. Any particular reason why the IPSL had a different trend, an opposite trend in the Bund area in some regions?
Yeah, so I had to look at, so of all the models, the main driver for each was relative humidity, except for the IPSL, it was precipitation. And so why that one has a different like main driver component, I don't know. So that's something I like within actually this week of creating those figures of the mean like 2020, 2060, like temperature, relative humidity. So that's something I still have to figure out, like why that one has such a distinct like climate driven component compared to the others. Because all of the others, relative humidity was number 1, followed by temperature, and then the ranking of wind speed, like the previous 12 months precipitation, was slightly different for each one. But the IPSL was completely unique. And why, I don't know. So, and I actually spoken with someone else who's doing prescribed fire work, and they were saying that they're having the exact same problem with the IPSL for prescribed fireworks. So yeah, so it's not just me, but like why specifically we were having this discussion, like why that one. Yeah, so I don't have a good answer for that yet.
Yeah, and that's interesting because the IPSL model is generally a hot and dry model for
I know. And so,
the country.
like I said, yeah, the fact that we're not the only ones having an issue makes me feel better, but why?
We have time for a few more questions. Please feel free to ask. Or comments.
Like, it's the only thing I can say also to other people is this is only the, as you saw, annual. It was like, you know, burn area per year, like fires per year. This model was run at a monthly time step, and so there is obviously within a year like seasonal things, so changing of timing. So similar to what Phil was saying, like whether like the return interval of fires. So there's a lot that can be done. This is just the first big chunk of that. And then also along with this work, we did the prediction of the probability of million-acre fires across in the future. So there's a lot more, again, with this data, but this is the final product of what I have so far.
Phil, go ahead.
Can along those lines, yeah, when can we expect to see the first iteration? And I apologize actually if you've already shared a publication and I missed it. But
No, it's actually right now. So it has morphed. Again, Phil's been around. He was sabbaticing in Jennifer Balder's lab in the beginning, so he saw this stuff a very long time ago. But it has been reiterated on quite a few times. And so right now, actually, Jennifer has my paper. It's PNAS formatted, cover letter, everything. So it's like it's I've been waiting to pull the trigger. So hopefully quite soon. But again, as you know, the review process. So we'll see. I'll let you know when it's done.
cool.
I see a comment from Joel Reynolds that an analysis of changes in season timing would be of interest.
Exactly. Yeah. So there's a lot more work to be done, but yeah.
Yeah, I just have a quick question that very, very, very interesting work. Just going back to that monthly. So you're running the model on a monthly basis, but so some of these seasonal patterns emerge, and are they only emerging because your different climate variables are just changing month to month, or are you actually putting in something in there that's telling you what time of year it is?
No, so just climate variables. Obviously, there's no like date like component. It's just based on, like you're saying, seasonality change of temperature, relative humidity, like
And then you're just to get the value yearly values you're showing, you're just summing, you know,
exactly. Exactly. So
Okay.
so the output, the summarized thing, I was saying like each model, like the output for the like count in the burned area is over 10 gigs like per model. So obviously like the output is quite huge. And then when you summarize like the CSVs, and so again we're taking the median run of those 2000 iterations. So there's a lot to be like summed down, but so I do have those monthly outputs. I just when it came to the top message first, we went with this rather than like seasonality changes. And especially since we knew we were trying like a short form like PNAS, we couldn't do the everything all at once in one big paper. So
Neat. Thanks.
As a co-author, I should not ask any questions, but I'll just put one. So looking at the changes in the east I'm wondering if we are underestimating the risk by just looking at relationship, historical relationship, even across much of the larger eastern region. What if we cross certain thresholds where it actually create even greater fire risk than what we are able to estimate based on historical relationships?
Yeah, especially with 84 on, like, in like looking at past stuff, especially like we're saying, like this is quite a recent past. Because some of the like the largest, deadliest fires, whatnot, have happened in like literally around the Great Lakes in like, you know, it was like 1880, like 4 or something like this. So like not still within like 100 years or so, like there are fires that have happened in places that we don't associate with fire anymore, but like burned over 1 million acres, like killed, you know, 700 people, and like burned like, you know, 17,000 structures and whatnot. Again, that's outside our recent observation, but like it just shows that these places have the capacity to have these huge fires as well. It's just, you know, again, our suppression and whatnot, we're not used to that in this like recent era. And so, as you say, we probably are underestimating future like capacity of fire in these places.
Sure, thanks. Yeah. Any last burning comment or question?
You can stop sharing. People can see each other's faces.
Well, I want to thank everyone for joining and having a great discussion toward the end. And Jilmarie, thank you again for a great presentation. And I can see a lot of comments in the chat, appreciating that, your work. So at this time, I'm going to turn off the recording. And thank you again for joining.